Look up at the night sky. The brilliant stars, the swirling arms of distant galaxies, the faint glow of nebulae is only a tiny fraction of what's truly out there. Everything we have ever seen, touched, or measured is made of what we call normal or baryonic matter. This is the stuff of planets, people, puppies. But the cosmos holds a profound secret. The vast majority of the matter in the universe, about 85%, is completely invisible to us. It does not shine, it does not reflect light, and it does not interact with our instruments in any familiar way. The first powerful piece of evidence for dark matter came from watching how galaxies spin. In the 1970s, astronomer Vera Rubin observed stars in the outer regions of spiral galaxies. According to our understanding of gravity, based on visible matter alone, outlying stars should move much more slowly. They should move slower than stars closer to the galactic center. Just like Neptune orbits the Sun more slowly than Mercury. But that's not what she found. Instead, stars on the outskirts were whipping around at incredibly high speeds, moving so fast they should have been thrown off into space. The only explanation, a huge, invisible halo of extra mass, providing the gravitational glue holding the galaxy together. A second, equally compelling line of evidence comes from gravitational lensing. Massive objects bend the fabric of space-time. When light from a more distant object passes by, its path is bent and distorted like a lens. Given that dark matter does not interact with light, how do we even begin to look for it? Scientists are employing a three-pronged strategy: laboratories deep underground, the vastness of space particle colliders. The first approach is known as direct detection. Building incredibly sensitive detectors placed far beneath the Earth's surface in old mines inside mountains. Thick rock shields, experiments from cosmic rays and background radiation. The hope: a rare dark matter particle bumps a nucleus, producing a tiny flash or vibration. Direct detection experiments are marvels of engineering. Vats of super pure liquid xenon, germanium crystals cooled near absolute zero, cleanroom environments stricter than surgical ORs. Scientists wait for years, hoping to catch one unambiguous collision. So far, tantalizing hints but no definitive signal. With no confirmed detection yet, the identity of dark matter remains a complete mystery, and scientists have come up with a zoo of theoretical possibilities. The leading candidate for many years has been a class of particles known as WIMPs, which stands for Weakly Interacting Massive Particles. These would be heavy particles that interact with normal matter only through the weak nuclear force and gravity. Their weak interactions explain why they are hard to detect, and their mass explains the extra gravity we see in galaxies. WIMPs fit the evidence well and arise naturally in some extensions of the Standard Model. However, years of searching for WIMPs have come up empty-handed, so other ideas have gained attention. One prominent alternative is the axion. Unlike a hefty WIMP, the axion would be incredibly lightweight, millions or billions of times lighter than an electron. Ultimately, why should we care about a substance we cannot see or touch? The quest for dark matter is about more than just satisfying scientific curiosity. It is about understanding our own cosmic origins and the ultimate fate of the universe. Dark matter is the invisible architect of the cosmos. Its gravity pulled the first wisps of gas together after the Big Bang, providing the seeds from which all galaxies grew, including our own Milky Way. Without dark matter, the universe would be a vastly different, more barren place, and the conditions for stars, planets, and life might never have arisen. To understand dark matter is to understand how we got here. The identity of dark matter is also one of the biggest missing pieces in physics. The Standard Model describes the visible world brilliantly, yet it says nothing about the substance that makes up 85% of the universe's matter. This is not a small crack. It is a gaping hole.